In this class, we will discuss uh, we will define Kirchhoff's laws for magnetic circuits. Kirchhoff's laws defined for magnetic circuit. Actually, Kirchhoff's laws are purely defined for electrical circuits. That is Kirchhoff's current law and Kirchhoff's voltage law. Your KCL and KVL. And these are purely, first of all, we have defined for electrical circuits. Then we will extend this the application of KCL and KVL. That is uh, KCL, KVL. That is Kirchhoff's laws. These two laws, when coming to the magnetic circuits, we have analogous. Why? Because for electrical circuits, we have parameters, electromotive force, current, then resistance. We have all these parameters, different parameters. We have analogous quantities in magnetic circuits, like magnetomotive force, flux, and reluctance. So, so then the conclusion is that if you can define Kirchhoff's laws for electrical circuits, namely Kirchhoff's current law and Kirchhoff's voltage law, then there should be an analogous Kirchhoff's laws, two laws again, for magnetic circuits also. So that is in that from that discussion we will come to the conclusion that Kirchhoff's laws can also be defined for magnetic circuits. Okay, now we will consider a magnetic circuit like this. That is, yes, this is our uh, some iron core we have. This is iron iron core. That means it will be a three-dimensional structure, iron core. Okay, and the front view of that three-dimensional structure is what I have drawn with. We have two windows, like, okay, two gaps, and this is the structure. Now this uh, this what we call is the vertical limb-like structure is known as the limbs of the core. Okay, vertical rectangle, vertical rectangles, and on so that we have one, one, two, and three. Total three number of limbs we have, and we are winding a, a coil on this limb, the outermost limb, like this. And current I uh, is is uh, allowed to flow through this winding in this direction, Now, according to the uh, Fleming's right hand rule, that is Fleming's right hand rule, Fleming's right hand rule, which is which you have studied in your plus 2 classes, I think. Fleming's right hand rule. That means the current, the four fingers other than your thumb. Okay, if you curl, then the direction of curl of those four fingers is the direction of current, and the thumb indicates the direction of flux, okay. For that means take consider your right hand, and you stick all the four fingers of your hand other than the thumb, and then you curl that four fingers, okay, four fingers. Then that curling direction will indicate the direction of current, okay, like this, the direction of current. And then the thumb indicates the direction of flux generated. That is what you mean by Fleming's right hand rule. So we have, if a current is allowed to flow into these number of turns, n, for example, it is having capital N number of turns, then at that instant what will be generated? A magnetomotive force will be developed. MF, magnetomotive force, or ampere turns, AT, will be generated, and that AT will be equal to NI. That is magnetomotive force. Now that magnetomotive force will drive a flux, and that flux will be like this. Direction of flux will be like this, okay. I'm considering only two flux lines, okay, two flux lines like this. And these two flux lines, actually it has got two paths to flow. That is, one path is, it can complete the path like this, right, in this manner. And the second path available for the flux line is like this. Okay, sorry, here it will be, it has got some correction. Yes, like this, and here it will be like this. Okay, yes, in this direction, in this direction, in this direction, and forms the closed loop like this. Okay, so yes, it is true, it is fact that there will be a last number, a number of that we don't know actually. A number of flux lines will be passing into uh, uh, into or through the two links. Okay, that is, this is limb 1 on which the winding is placed. This is limb 2 and this is limb 3. Okay, and so we are we are considering only two flux lines for the time being, for the better explanation of the concept. Okay, actually there will be a large number of flux lines produced by this uh, magnetomotive force, ampere turns, due to the flow of current I through the n number of turns. So there are two possibilities. That what I am trying to convey to you is that there are actually two paths for the flow of flux lines. One path is uh, from limb 1 to limb 2, and coming back to limb 1, and the second path is from limb 1, okay, and uh, flowing into the limb 3, the outer limb, and then coming back to limb 1. So these are the two possibilities, two paths of uh, paths for the flow of flux lines. That means the yes, now you think uh, these these flux lines or fluxes in an electrical circuit. In an electrical circuit, the fluxes are analogous to the current. Flow of flux means flow of current. So current is flowing in two paths means uh, in two paths means the current got divided into two paths means the two paths must be connected in parallel like this, right? So current, so like this. So that means IT, total current IT, and I1, I2, right? In this manner current will be divided. So the same process is happening in this magnetic circuit also. So you can define here two paths, that is one, okay, one, and yes, path means I am naming it as this limb is P, and this the horizontal section is Q, and this limb 2 is R, and this horizontal section is S. And another path is and PQ, and this horizontal section I am calling it as T, and this limb 3 is U, and this again horizontal section V. So we have two paths, that is one path is P, Q, R, S, and P, like this, P to Q, then R, S, and coming back to P. And the next path is P, Q, okay, P, Q, then T, U, V, S, P. That is T, U, V, S, and finally coming back to the same starting point P. So these are the two paths in which two fluxes are flowing. So the amount of flux, actually the amount of current in an electrical circuit, in a current dividing circuit, depends upon, let us say this is resistance R1 and this is resistance R2. So I1 and I2, magnitude of I1 and I2 depends on resistance R1 and R2. That means if R1 is less than R2, R1 less than R2, that means opposition is low in this path. So that means I1 should be greater. I1 will be greater. I1 will be greater than I2. So that means the current always uh, looks or choose uh, the minimum resistance path. Okay, yes. So in the same manner, the magnitude of flux here, for example, this is 5 5 5 1, okay, and this is 5 2, like your I1 and I2. We have phi 1 and phi 2 here. So the magnitude of phi 1 and phi 2 depends upon the resistance. Here it will not be resistance, it will be reluctance. Okay, so the phi 1 and phi 2 magnitudes depends upon the reluctances offered by the this path PQRS and the path PQT, U, V, S and P. Okay, these two paths. Okay, so we are going to model this magnetic circuit as, yes, we have MMF like your EMF, yes, EMF in an electrical circuit, that is here we have MMF. Okay, and we have two oppositions, two reluctance, that is S1 and S2 we have, and we have phi 1 and phi 2, two fluxes, and the total flux is phi t. Okay, so hope you understood. So uh, in this example, electrical circuit example, it will be not it will not be current source, and it will be your, it should be your electromotive force EMF, 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 E. Okay, so this figure 1, this is figure 1, this circuit and this circuit, figure 2 circuit, if you observe, these are the analogous circuits. Okay, that means I will draw once again. That is, we have, okay, EMF E we have, and we have two oppositions to the flow of current. So it will be resistance R1, R2, and this will be I1, and this is I2, and the total current is I1 plus I2, that is I total IT. Okay, so we have this analogous transformation, that is IT is transformed to phi t, I1 transformed to phi 1. Okay, and this resistances R1 R2 transformed to reluctances S1 and S2. Okay, and this EMF battery voltage EMF is transformed when coming to the into a coming to a magnetic circuit. It is transformed as magnetomotive force MMF. Okay, this is the so yes, once you have the electrical magnetic analog of the the electrical analogs of the magnetic circuit. Okay, then uh, your what we will do in your electrical circuit is that you will apply, yes, KCL and KVL. You will identify the nodes and you will apply KCL here, and also you will apply KVL by identifying the two loops, right? So in the same manner you can apply uh, what Kirchhoff's current law in magnetic circuit. That means Kirchhoff current is replaced by Kirchhoff's flux law. Flux KFL, Kirchhoff's flux law, and KVL is Kirchhoff's voltage law uh, in an electrical circuit, and when coming to a magnetic circuit, it will be Kirchhoff magnetomotive force law. That is Kirchhoff MMF law. MMF law. Okay. Yes. So yes. Once again, then we are going to apply these two laws. That is KFL and KMMF law. Okay. For a magnetic circuit. That means yes, apply here I'm going to apply KVL in for this magnetic circuit. That means we will get what we will get is yes, this is plus, okay, and this is minus, and here phi 1 in this direction, so it will be plus minus here, right? Okay, here it will be plus minus again. So I have identified two loops here. I have identified, so this is loop 1 and this is loop 2, and we have mmf 1 here. Okay, that is I am denoting it as 80, 81 and 82, 82. So yes, I'm applying K mmf Kirchhoff magnetomotive force law for the loop 1. So what happens is as mmf that is 81, okay, plus 81, okay, then minus plus minus, yes, minus 4 minus 82 equal to 0. That means 81, okay, 81 minus 82 can be substituted by S51 into S1 equal to 0. That means 81 equal to 51 S1. Okay, this is yes, what is your Kirchhoff law in a magnetic circuit. So similarly, you can apply the Kirchhoff uh, current law in a magnetic circuit. That is Kirchhoff flux law. That means you are identifying the node. Okay, here the node N. Okay, so we have phi total in this direction, and my convention is in this direction. That is I'm in all the problems I will be assuming all the currents are leaving the junction, leaving the node. Okay, so as per my convention, this is the direction, these are the directions. So that means actually phi total flux is in this direction, so how to take negative of that. That means minus 5t, okay, plus yes phi 2 plus phi 1 equal to 0. That means phi t equal to phi 1 plus phi 2. So yeah, this is the Kirchhoff flux law, and this is what is your Kirchhoff magnetomotive force law. So that is the Kirchhoff's laws in a magnetic circuit. Okay, so I hope you understood. Now let me consider another example, another model of a magnetic circuit. Okay, another figure like this. the uh, same figure, the same three-dimensional structure I am taking. And that is it is again made up of iron material, okay, iron frame, you can say. Okay, and that means this is these the vertical columns, vertical structures, rectangular structures are known as the limbs of this whole structure, and this is known as the frame of the whole structure, the horizontal and the horizontal frame, yes, upper frame and the lower frame, two frames, and one, two, and three limbs. Okay, this is my three-dimensional. This is actually, you imagine like a three-dimensional structure. Okay, now in the previous case, we have considered a coil which is wound on this limb, third limb. Okay, and now I'm considering the same coil, number of turns, having number of turns capital N, and the current I is flowing through that coil. So that is wound in this manner on the limb number 2. So I okay. Now again I'm applying the Fleming's right hand rule. Okay, so that the four fingers, if you curl the four fingers of your right hand, if you curl inwards, then the thumb direction indicates the direction of the flux coming out of that winding. That means like this, flux will be coming like this. Flux, and this is I'm calling flux phi amount of flux like this. So, and the magnetomotive force here will be having a magnitude of f equal to n into I, ampere turns. Now, the moment the Ni, magnetomotive force, is set up, then it will drive a flux, or it will force the flow of flux phi. Okay, then this I'm considering 2 points, point P and point Q on the limb number 2, on which the coil is wound. Then the flux of phi is flowing, okay, is actually flowing inside this coil. That means an opposition is also offered by this limb 2. An opposition is also offered by this limb 2, because the flux of phi is initially it is going upward, and that means it will experience some opposition in this limb also. Okay, so let this yes, that opposition, that is what we will call it as reluctance of that limb. Okay, suppose I'm having this reluctance, that is opposition, on offered by the limbs and the frame. All these are different. Okay, that means here we have S1 reluctance offered by this path. Actually, yes, first of all, phi, this is total flux of phi. Then what happens is, for phi to complete a closed path, here we have phi is having two possibilities to flow. There are two paths to flow, for the flow of the flux of phi. Flux phi, right? So that means it will flow, some of the flux lines of the total flux setup will flow in this manner, or it will take a path like this in this manner, and some of other flux lines will take path like this. Sorry, path, the shortest path. Okay, shortest path possible, like this. My drawing is not that much good, that is why. Okay, so there are two possible paths for the flow of flux of phi, and the amount of flux lines flowing in these two paths will depend upon the reluctance offered by the two paths. Okay, that means, from I'm naming it as P and Q. We have considered 2 points inside this coil. Okay, and uh, we have another point PR here, and S here, and T here. And similarly, we have, in this path we have U point here, and a V point here, and U S U V W, yes, W point here. Okay, so let us assume that the reluctance or the opposition to the flow of flux line. Okay, there is this flux lines, let us call it as phi 1, and this flux line is phi 2. So the flow of flux phi 1, we have S1 reluctance, and for this path we have S2 reluctance, or S2 opposition. Okay, so this path, Q, R, S, T and P, again Q, this closed path is having a reluctance S1, and again the other closed path, that is Q, U, V and W, this much path. Okay, this much path, only this much path, that is Q, U, V and W. Similarly, on the other side we have Q, R, S and T. Okay, this much portion, that means the portion excluding the winding portion is having reluctances S1 and S2. Okay, now, for the flow of, in order, actually the flux lines are always form the closed path or closed loops. So the flow of flux phi, total flux phi, okay, inside this coil winding is also having some, or is also experiencing some opposition also in this, from this limb 2 also. So that reluctance, that is, that I am denoting, naming it as S reluctance. So our model will be like this. I am representing the reluctance like resistances, okay, because these are analogous quantities of electrical and magnetic circuits, and uh, I will be representing the magnetomotive force like a battery, and current in electrical circuit, that is flux here. Okay, so what what the magnetic circuit looks like, the model of the magnetic circuit looks like is like this. Yes, first of all, magnetic motive force like this. Okay, mmf, and then the reluctance offered by this limb 2, that will be like this, that is S. And then we have two paths. Then that means that the total flux of phi is divided into two parts. That is, one will go to the right side and one will go to the left side. Okay, and it will come back to this uh, at the same point also. So that means it depending, there will be two oppositions for the flow of flux, phi 1 and phi 2. So that means it will be a parallel there will be a parallel combination like this. Yes, this is S1, and on the other side I have, sorry, this is S2 and this is S1. This is S1. Okay, and I'm naming this is phi, and I have here a phi 2, and I have here phi 1. Okay, this is the modeling or the representation of this entire magnetic circuit. Okay, yes, this is another example for the modeling. Some of you might have some doubts in your mind, like, sir, this whole structure is made up of iron. So how the two parts will exhibit or will offer two magnitudes of reluctances S1 and S2, and here S. How it is possible? How it is possible, I will explain. This actually, these two parts, okay, we have the reluctance equation S. In general, we have S is equal to L by mu 0 mu r into A, right? So if these two parts have should have two reluctance, two values for reluctances, then uh, the on comparison, either L mu or mu 0 or mu r or A or other some combinations of these four parameters, or all should vary. That means it should be different for if either any one of the parameter or all of the parameters of for these paths, for these two paths is different. Okay, then the reluctance offered by the two paths will be different. So in this example, actually the distance, yes, there are many possibilities. That is, iron is our material. So for material iron, actually this mu 0 is constant. This is a constant value, that is 4 pi into 10 power minus 7. This mu r is also constant. Why? Because the material we are considered is made up of iron. So for a material, the permeability, relative permeability must be a constant value. and it is a constant value. So mu 0 and mu r are constant. So its product will also be a constant value. Right. Now the cross-sectional area. The cross-sectional area of path uh, 1 will be like this. Okay, this is A1 and this is A2. So there is a chance that this A1 and A2 must be different. Okay, the area of cross section can be different. So if these two paths are having two different cross sectional areas, then what happens is one should have A1 term and one should have A2 term, so that S will be S1 and S2. Two different values will be there. Right. Now another possibility is that you might have these two paths might have different magnitude of lengths. That is, the distance traveled by this flux phi1 and phi2. Okay, that is the length. So it may be, yes, it may be higher or lower for the two paths. So in that manner also, the reluctance of the two paths will vary or will be different. Okay. So, and even if all these parameters are same, suppose we have the same length, okay, same length for the first path and also same length for the second path, okay, and also your cross sectional area A1 and A2 is also same. Okay, in such situation what happens is S1 will be equal to S2 and that will be equal to S. Okay, that means the yes, S1 must be equal to S2 and that will be equal to S dash actually, not will be not equal to S, and S dash not equal to S. Why? Because S is having a length this much, only this much length. Okay, but the cross sectional area is same, that is A for this limb and A here for the path 1 and for the second path also is having the same cross sectional area and also made up of the same material, that is iron. So the different parameter is only parameter differing is L, length. Okay, so S1 and S2 will be equal and that is equal to S, but that is equal to S dash, but it cannot be equal to S value. So so our circuit will be, our model will be changed to like this. Model will be like this. Okay, this is like this. This will be S dash and this will be S dash and this will be S and this will be MMF. And here let us say that this is phi total is the flux, then this phi total will divide equally in this case, that is phi 1 and phi 1 again. Okay, so the phi total will be equal to phi 1 plus phi 1, that's equal to 2 phi 1. Okay, so that will be the difference. Yes, now I would like to discuss another magnetic circuit, another type of magnetic circuit like this. Okay, I'm considering a core like this, and this core is made up of say iron, and in between we have air as the material, and I am I have Si and N is the number of turns. So I have wound a coil like this. So no doubt that MMF will be set up, and that MMF will drive a flux phi. Okay, that a flux phi like this. Flux phi, it will be many number of lines actually, but I'm taking only one line. Okay, like this it will be flowing. So and this the magnitude of this flux can be find out, okay, like this. That means this phi, actually this phi on or on completing a closed path like this, okay, it will it will come across two type of materials. The first type of material is iron, and the second type of material is air. Okay, and this iron will be having a reluctance, that is SIN, that will be equal to L divided by mu 0 mu r into A. Okay, that means L will be L1 and A will be A1, that is this cross sectional area A1, and L means the yes, this length up to here. Okay, this length. Okay, and L1, that is, and then mu 0 is a constant for pi into 10 power minus, and mu r for iron it will be some 1000. Okay, so S iron will be a constant value. At the same time, we have an air column like this. Okay, an air column I'm considering like this. So if you consider an air structure like this, it will be having an area of a cross-sectional area, the same cross-sectional area as that of iron, that is A1. But the length is different. Some L2 will be there. Okay, length of that air column will be different, that is L2. And also we have mu r will be equal to 1. So the reluctance offered by the resistance will be the reluctance offered by the air will be SI. We can name like this. So this SIN and SIR are in series like this. This is SIN and this is SAR. Okay, like this. And the magnetomotive force here, it will be like this. I'm representing it is like this. So this will be our magnetomotive force MMF, and flux phi will be like this. And two materials which are in a series manner, placed in a series manner. So the magnitude of flux phi will be equal to mmf divided by SIN plus SAR. So this will be the magnitude of the flux. So this is another magnetic circuit. So in this manner you have to model, or you have to write the analogous of of the magnetic circuit, and and then you can find phi. Okay, by applying your Ohm's law. Okay, Ohm's law, or you can apply KCL, KVL. Okay, but KCL, KVL, Ohm's law, all will be all are analogous to this magnetic circuit.